Rebecca, could you start recording? Okay, great. Okay, so it's my pleasure to introduce to you Rebecca Sheppard today, who will be giving a talk on not your usual circle geometry on the integer grid. So just I would like to say that Rebecca was a master student with us, Anne and myself, at the University of Liverpool, and now she is our PhD student with Anna, myself, and also James, but in University of Manchester by some reason. So anyway, so Rebecca, you're very welcome.
Okay, thank you for the introduction, Alag. So, as Alag said, my presentation today is not your usual circle, geometry on the integer grid. So, when you're thinking of a circle, you are probably thinking of an object similar to this, or the outside of this. But that's not the object that we're talking about today. So, the object that I think of when I'm talking about a circle in integer geometry is an object which looks similar to this on the screen now. So, in this presentation today, I'm going to discuss geometry with integers. I'm going to discuss integer circles and their densities. And I'm going to then move on to intersecting integer circles and their densities. So, first I'll introduce integer geometry. So, in integer geometry, two objects are considered the same or integer congruent if there is a lattice-preserving affine transformation or a translation between them. So on the bottom, I have some triangles in integer geometry, which, while I'm talking, you can think if they're the same or not. So I'm just going to go through some properties. I'm not defining these properties, but some properties are integer length, which I will later define, integer distance, and integer angles. So these triangles here, they are, in fact, integer congruent to each other. So you can see that this length, we can map this length to this length. So this length on the bottom, this side maps to this side and this side. And we can also say it maps to this side here. Now this side here, we can say it maps to this side, and this side here. And then the other sides map to each other. So the integer length is the same. You can get a sort of intuition for that. There's no included integer points other than the vertices on this side length and this side length, but there is one included on this side length. And I didn't mention integer area here, but you can get a sense for integer area as well. You can put 3 empty triangles. Empty triangle is triangle that doesn't have a point in the center of it. You can, not 3, sorry, can't count. 1, 2, 3, 4, 5. You can, but there's the same number of empty triangles that make these up, and integer angles have to do with these angles, the sales of these angles. So the sale here is just this line down here. The sale here is this line here. The sale here is this line here. And the sale here is one of these lines. I can't quite visualize it at the moment, but it's the same angle. And you can do that for all of the angles. I just did the example for one angle. So moving on to some nice definitions. So if we let A and B be integer points, then the integer length of AB is 1 less than the number of points, integer points, contained within the closed segment AB. So here we have a closed segment. We have segment AB. So there's 4 points. So the integer length of AB is 3. And we remark that the integer distance of AB between A and B is equal to the integer length of AB. This isn't a distance in the metric space sense, but it's a distance for, we just use the term distance to describe it, because it makes the definitions of circles nicer. And it has a nice relationship with the greatest common divisor. So if I consider the coordinate points of this A and B, the greatest common divisor of this length here, the change in x, and the change in y, is the same as this integer length and this integer distance. And a similar definition occurs for higher dimensions, but we're not. In this presentation, I'm focusing on the 2-dimensional case. So an integer circle is the locus, that's S or O, is the locus of points in x in z squared, z2, such that x belongs to the integer circle if and only if the distance between x and the point O is r. So here r is the radius of our integer circle, and O is the centre of our integer circle. So I have some pictures here. So on the left, we have the picture we had from before. This is called a Fourier starburst, and we get this by joining up the points which are on our integer circle, and I've coloured in the interior. And on this, and on this figure here, we have just the points on the integer circle. If you notice, the figure on the right has a few more points included. They're the bolded points than the Fourier starburst, and that's because we're a bit zoomed out. So from here we're going from -5 to 5, and here we're going from -10 to 10, and we have more points included as we have zoomed out. We can, in fact, zoom out arbitrarily. So on this figure here, we have from -100 to 100, and as you can see, there are lots more points. So we get the sort of intuition that this set has an infinite number of points, and it's not bounded, they go everywhere. So how do you measure something like this? So one way that you can measure it is to take the notion of a density. So the density of a set A is the proportion of points in A to the proportion of points in Z squared. So just the fraction of included points. To get this definition to be more formal, I'm going to have to introduce another definition first. So a filtration is a sequence of subsets Sn such that each set Sn is a subset of the next set Sn plus 1. And an exhaustive filtration is a filtration which satisfies that the limit of the union as n goes to 1 to infinity of these sets Sn is, in our case, Z squared, in a more general case, just whichever set you have a filtration of. And I'm going to introduce the formal definition of density now, which is that the density of a subset of Z squared, with respect to a filtration Sn, is the limit as n goes to infinity of the number of points in the intersection of A and Sn over the number of points in Sn when this limit converges. When this limit doesn't converge, we just wouldn't have a density. In this presentation today, I'm going to be using this filtration, which is math cal I, which is of terms in, and these are just squares from -n to n around the origin intersected with Z squared. We've got closed intervals here, so it's including the boundary points. We notate the density as a hash symbol. In the lowercase, we have our filtration here, curly I, and the name of the set A. This is one of the terms in our filtration, and as we go through this little animation, we can see how this filtration grows, and you can intuit that this is exhaustive. It will eventually cover all of Z squared. So the theorem is that the density with respect to this I of a unit integer circle centered at a point O is 1 divided by the sum from n is 1 to infinity of 1 over n squared. If you're familiar with number theory, you'll know that this thing on the inside is the zeta function. So this is 1 over the zeta function of 2, and that is 6 over pi squared. That's known from the Basel problem. This, in terms of geometry, is proven in terms of two lemmas. Just this first equality that this expression gives this. This next, where it's in terms of zeta function, just comes from the definition of zeta function, and the next is Basel problem. So this first equality, we have the lemma that the density of an integer circle of radius r is the density of a unit integer circle divided by its radius squared. We can sort of intuit this by picturing that we're scaling. We multiply everything by r this way, and everything by r this way, and that, in general, when you look at a subset of Z squared, you'd get, on average, r squared less by a factor because you stretch it out. So that's how we get that. And then there's this other lemma, which is that the density of the union of all integer circles with radii in the positive integers centered at the same point is 1. This is because every point has a integer distance from the origin. So this set here is the Z squared set minus the origin. Well, set minus the center of our circles, which might as well be the origin, without loss of generality, and that the set complement to a finite set has density 1. Now, since this density is greater than half, we know that the density of the intersection of two unit integer circles is greater than 0. Just a little remark, we can use the density of one integer circle combined with the second lemma to get the density of an integer circle of any radius. So on this figure, we have pictured in purple dots, we have every dot on this screen belongs to the union of the intersection of integer circles centered at the large dots. The purple dots represent points which are on the unit circle centered at the purple dot, but they're not on the unit circle centered at the green dot. And the green dots, likewise, they're on the green integer circle, but not on the purple one. And the large black dots represent points which are on the intersection of the integer circle. This is a finite subset of that, but if we zoom out a bit, you can see the pattern that it sort of forms. We have these rays here, but overall it looks dense. This picture intuitively matches with what we know to be true from the theorem. I've removed all of the small purple and green dots here so we can just see the intersection rather than the union, and we can just appreciate its pattern. If we change the centers, it does look different. So we can intuit that the distance between the centers, or just where the centers are located, may change the density, since these pictures look different. And if we take them even further away, we have another picture, which again looks different. And if you sort of squint your eyes at them, you can get a visual guess at the density, but we don't want a visual guess, we want some formal definition. So if you let A and B be points in Z squared, then there exists a rational number D such that the density of the intersection of unit integer circles centered at A and B respectively is this rational number D times by the product for P in the prime numbers of 1 minus 2 over P squared. More specifically, we know what this rational number D is. It depends only on the integer distance between the centers. This we can intuit because we could move any two centers, any segment to any other segment of the same length using our affine transformations. So this means it's nice and geometric. And this is given by the function d of d, which satisfies for prime numbers, d of p is p squared minus 1 over p squared minus 2. For prime p again, we have that d of p to the k is equal to d of p for k in the integers, in the positive integers rather. And for coprime m and n, we have that d of mn is equal to d of m times d of n. This is a property known as being multiplicative. And knowing how a function behaves on powers of primes and on multiplicative numbers, we know how it behaves on integers, on positive integers. So here's the Mobius function mu. In order to sort of outline this proof, I'm going to introduce a few concepts from other areas of mathematics. So the Mobius function mu is defined so that mu of 1 is 1, mu of a product of p of n distinct primes is minus 1 to the n, and mu of p to the km for k greater than 1 for any prime number p is 0. So Mobius function gives 0 when we have a repeated prime number. There's the number of divisors function tau, which says the number of divisors that this has. The square brackets, so if there is a true statement in square brackets, this returns 1, and when there's a false statement in square brackets, this is 0. And we use big O notation. So big O notation formally means that positive real number m, such that for large enough x, the absolute value of O of f of x is less than or equal to m times by the absolute value of f of x. More formally, less formally rather, this is a way of describing how a function behaves asymptotically. So, recall the theorem from before. There exists a function d of d such that the density of the intersection of unit integer circles centered at A and B is d multiplied by the product of prime numbers between 1 and 2 over p squared. Now, the idea of the proof is that we let d equal 1. I'm just going to let d equal 1 for the time being. At the end, I'll discuss the case when d is not equal to 1. So we consider the points which are included in a subset of z squared. I'm going to use the positive in 1 and r, so it's one of these terms in our IN, but only positive. We can do this because of some level of symmetry. So we have the sum for x and y belonging to the intersection of the interval 1r and z, where in square brackets, the greatest common divisor of x and y is 1, and the greatest common divisor of x minus 1 and y is 1. So we're counting points in which the greatest common divisor of x and y is 1, and the greatest common divisor of x minus 1 and y is 1. This is because of the link between the greatest common divisor function and integer length, allows us to express it this way. This is the same way of saying the integer distance between a point xy and the origin is 1, and the point xy and the point x minus 1, y is 1. So here this is equal to this expression, so we take d1 and d2 belonging to the same set as 1 and r belonging to, and we say that these are coprime anyway. Then we have that it's r mu of d1 d2 divided by d1 squared d2 plus o r log squared r. There's a lot of number theory that we did to get between this point and this point. So now we take the limit as r goes to infinity, and we divide by r squared. We get that the density of our intersection of two unit integer circles with respect to the I filtration is the sum of d equals 1 to infinity over the sum of d1 and d2 product to d multiplied to d, and these are still coprime, of mu of d over d squared. To remove this term of d1 and d2 multiplying to d and the greatest common divisor being 1, we can introduce a factor of the number of divisors function. So we have the product for d equals 1 to infinity of mu of d, tau of d, divided by d squared. If these d1 and d2 were not coprime, mu of d would give 0, so this is adding a 0 term to the sum, which doesn't do anything because it's completely convergent. And the tau of d allows us to count for every combination of d1 and d2. Since it is completely convergent, we can rearrange it. So let's say we express it as a product and rearrange it based on the prime factorization of it. So you have the product for p belonging to prime numbers of 1 plus mu of p tau of p over p squared plus mu of p squared tau of p squared over p to the 4 plus and so on. This is the product for p in the prime numbers of 1 plus mu of p tau of p over p squared, since for repeated primes this mu gives 0. Since p is defined based on, p and tau are both defined based on the prime divisors, we know that mu of a prime number is -1, and we know that a prime number has two divisors, itself and 1. So this is the product for p in the prime numbers of 1 minus 2 divided by p squared. This is where we got the coefficient for. Now for d larger than 1, we follow a similar proof. When I went through it, we considered it for prime numbers. Then we considered it for powers. Then we showed that it's the same for powers of prime. And then rather than showing it explicitly for composite numbers, we showed that d was multiplicative based on some of the properties of divisors. So in the project, my master's project, that's what this presentation's based around, I studied notions of density and integer geometry. I studied the densities of integer circles, and then we conclude by studying the densities of the intersections of integer unit circles. And some further questions moving forward include asking if density is a geometric invariant. So it was for integer circles, and it seems to be for the intersection of two unit integer circles, but more generally for the intersection of n unit integer circles, or just n integer circles of any radius. Is this a geometric invariant? What are the properties of this number here? Can we express it in a different way? That's the product for p in the prime numbers of 1 minus 2 over p squared. That's the irrational coefficient. Similarly, we can look to see if there's a similar irrational coefficient for other numbers of intersecting circles, which we have done some work around. And we can consider the high dimensional case. So we consider what the density of the intersection of integer n spheres is. I've just written a few references that are relevant to this project on the slide now. So there's the preprint, circumscribed circles in integer geometry, which is expected to be in the next edition of the Annual Mathematical Journal. There is the book Geometry of Continued Fractions. There's the book An Introduction to the Geometry of Numbers. And there's proofs in the book. This proof in the book has a nice proof of the Basel problem if you're interested. So thank you for coming to my presentation. If you have any questions, I will take them now.
Okay, so please, any questions, comments?
Sorry for the slightly shorter talk. This presentation was originally for a competition which wanted shorter presentations.
I have a question maybe to start out. These terms, are these just for unit circles or, sorry, yeah, unit integer circles or any integer circles?
The terms that we currently have, these, let's find it. This expression is only for unit integer circles. It's not been proven yet, but we have conjectured and nearly proved that it is a slightly different case for when it is non-unit. Rather than having the prime numbers here, we'll have some set which involves certain prime numbers and certain powers of primes, and this expression might look a little different, but we product over powers of primes for arbitrary integer circles.
Yeah, just to say that, I mean, in fact, it would be also some function times the same product, but that function would be much more complicated. So let's put it like that.
Yeah,
so the function,
any real number can be expressed as some function.
So I mean, in a way, it's a very surprising result because so it looks like that these intersections, even if they are with different distances, right, different radii and different points, they actually share the same irrationality. They differ only by some rational coefficient.
Yeah,
it's quite surprising actually. So maybe could you show one more time the pictures of of the circle?
Of the intersection of circles,
yes, this one. Yeah, just what I want to say that these numbers, the number of these densities of these points, yes, so this next one and next one, right? They are the same up to some rational constant. So it's quite surprising, isn't it? Because I mean, so also one funny thing that for now we have no idea what is this irrational number. So that's actually a conjecture, not a conjecture, but a problem. So is it possible to write it in some form of zeta functions or something like that? Maybe Bessel functions, I don't know. So it's like for the simplest case, like for when you have 2 points close to each other, right?
It can be written in terms of the Fellatournier constant, but the Fellatournier constant also has a strange expression for it. It just also has a name.
Right. And also, of course, we are working on more than 2 points as well. So it's our subject here. So, well, I mean, in general, so the strategy of this talk this investigation, let's put it like that, was that we would like to build a comprehensive, well, geometry, like standard geometry for for integer lattice, yeah. And once you are doing this, you have inevitably to come to circles, and the intersection of circles more or less the first thing to study. So that's just the first steps in this very long subject, I would say. Right.
Sorry?
Yes, Mati, please.
You mentioned these fiery sunbursts at the beginning.
Yes.
These are almost like finite, almost like approximations of the integer circle in some sense. But they have an interior. You can create a boundary of them.
You can create a boundary.
And I wonder, is there any relation or connection between intersections of these boundaries or interiors for different integer circles? Say for, I don't know, certain radii of these sunbursts, if that makes sense. Have you studied any connection between these sunbursts and these integer circles and densities at all?
No, the sunburst would depend on the particular term in that you're taking, but that's an interesting problem to look at.
Well, I mean, I would like to add here that sunbursts are defined in the box n times n, which is not invariant under cell to z transformation. Therefore, your question is not in integer geometry, unfortunately.
No, well, it's more a question about any connections between integer and Euclidean geometry. And on that point, you call these integer circles. And I have a question about the not validity of the name, but the how closely do these resemble circles? In the sense, well, the sense I was thinking about is circles can be used to define curvature, and in a discrete sense.
Yeah, there's not an SL2Z integer geometry definition of curvature yet. There are some people, Oleg's one of them, who are interested in defining a differential geometry and a notion of curvature in integer geometry, but the current notions of discrete curvature don't relate to integer geometry in any way. I would be very surprised. So
the question then is to come up with an appropriate sense of curvature that relates to integer circles in the same way that curvature in Euclidean space relates to Euclidean circles. Have you thought about this, either of you?
We are working on this, to be honest. So
okay.
And so, I mean, to say even more, James Dolan, who is also here, so he is, so we basically, there is a paper on classification of n-gons via continuous fractions, and there we have already used one of the versions of curvature. However, it's not related to circles at this moment, so it's not really the answer you would like to know. But what I want to say is that we already use something which is needed. So basically, curvature is some integer invariance dependent on 3 consecutive points, right?
Mm-hmm.
3 or 4, yeah. So depending which type of curvature you are looking for, right? Yeah. By the way, James, are you here?
Yeah.
So, can I ask you? I think you haven't yet done a talk about this paper in our seminar.
No.
So you see, it's very nice that we managed to get you here. So I know that you will be having Viva very soon, which is really great. So do you want to train your talk here for the seminar before Viva?
Yeah, sure. I've not got like the scope of the talk yet from David, but I think I should soon. Yeah.
Yes. Basically, the talk would be like the ones you give on the conferences. So it's really great, and I think we would be really happy to hear it, because it's precisely very, very well in line to today's talk, for instance. Okay.
Yeah.
So great. So we have several dates which are free, starting from the next one and afterwards. So do you think if you would be ready to do it next Wednesday?
I don't think next Wednesday. No, I've got some stuff over the weekend I'm doing. So.
Right. So in 2 Wednesdays.
Yeah, I think I could do that.
Excellent. So therefore it's fixed. That would be amazing. So we're a little bit, how to say. By the way, if someone has a nice candidate for the next Wednesday talk, so you're very welcome to write me an email, please. So so we have some local logistical problems, so therefore some of the talks we will be missing in the next weeks. But if someone is ready for a fast talk, please let me know. So right. Okay. Yeah, so some further questions to Rebecca.
Okay.
Okay, so if this is not the case, then I think I think that's it. So Rebecca, I think you can stop recording then.
Okay. If anybody does have any further questions later down the line, feel free to email me. I've got rshep@liverpool.ac.uk and rebecca.sheppard-2@postgrad.manchester.ac.uk.
All right, so I have just comment